Hello and welcome to a short, not necessarily short seminar on the biostatistics part of the biophysics final. My name is Musa Mustafa, and I'm gonna be showing you through how to handle this part of the oral final of the biophysics final. So first thing to highlight is that this part is very easy, but you just gotta know what you're doing. If you are able to nail this part, do keep in mind that this is 1/3 of the oral. The oral has 3 parts, and this is 1/3 of the oral, and it's very easy, and it's a really big boost to like the final as a whole if you're able to get this point right. Like the examiner will be a lot happier with you, So if you want your exam to go smooth, if you want to draw a nice big smiley face on your examiner, then know this part, because really it is not difficult at all. As soon as you get the hang of it, it is really smooth. So that's exactly what we'll be doing. We'll be covering, first off, we'll be covering some theoretical points, which you will need to know so that you know up from down. And then we're gonna practice like the points themselves, like step by step. We're gonna go through the Excel part so that you know exactly what you'll have to do during the final. And without further ado, we'll head right to it. So what even are you doing? What is this biostats part of the biophysics oral? So it is a part focused on hypothesis testing. So what is hypothesis testing? It's really simple. It's simply gonna be you are testing a hypothesis, okay? Just some quick points before we continue. Actually, I wanted to mention that what you'll need to follow with the seminar is this file right here, this document. It's called Biostats Excel file, Word document. I'll put a link on it in the description of the video. You'll also need this file right here. It's called Excel Instructions 3.pdf. You'll find it on Moodle for biophysics, and you'll also need this file. It's called Excel 3. You'll also find this on Moodle. So the PDF file, the Excel file from Moodle, and this Word document just to follow along in the video description below. You don't even necessarily need to you don't need to have this now, but you should download it afterwards just to revise like some nice definitions, some nice points are mentioned here. Anyways, without further ado, so what is this? This is hypothesis testing. Hypothesis testing. So what is it really? You're just testing a hypothesis. You've got some sort of hypothesis and you are testing to see whether it is true or not. All right. So this hypothesis is basically some sort of like default idea you have about something, and you want to check whether and you want to test whether it is true or not. So it revolves around wanting to test if the default idea you have about something is true. Okay, this default idea is known as the null hypothesis. Okay, it is the null hypothesis. This is the hypothesis that you are trying to test. And it's very important to know this definition, because in the exam, the examiner will ask you very likely to define what is null hypothesis, especially if he sees that you're a bit confused or something like that, because he basically wants to understand, do you even know what you're doing? And this is thusly very important just to know what you're doing. You are testing a hypothesis. This is null hypothesis. Null hypothesis is the default idea you have about something that, and you want to test whether this hypothesis is true or not. So the example of a null hypothesis is basically you hypothesize that the population of males in Czech Republic, their blood pressure average is 110, for example. Okay, the average blood pressure of a male in Czech Republic is 110. That is your default idea about the males of Czech Republic, okay? And this is thusly your null hypothesis. Your null hypothesis, you call it like H0 is what we call it, null hypothesis. And you say that your null hypothesis is that the average equals 110, okay? And then you would be testing to see whether that is true or not. And how do you test this? You basically take a sample of male Czech Republic people, male Czech Republic people, and you check their blood pressures, and you check the average of their blood pressures, and you want to see whether this sample is saying that this case is true or not, whether the average of the sample is indeed telling you that like the average of the sample is indeed like 110 or around near 110, And if it is, then you're more confident that that the average of the population as a whole would be 110. That is the basic gist of it, okay? A few caveats to add to this. Okay, just points off the top of my head that you'll find interesting and that you'll find useful along the way, just for understanding. That this sample that you take of males of Czech Republic, you don't want them to be total fringes. Like, you don't want them to be on the in any extremes. You don't take the highest, the top 10 highest blood pressure people in Czech Republic and you use them as your sample. No, you have to have a very normal sample. You have to have a very normal, very typical sample. And what helps to get a typical random, like a typical normal sample, is that you make it a random sample and you don't make your sample too small. You make it of decent size and you make it people who aren't on extremes, like, you know. So that is the gist of it. And basically, so whenever we want to take, now none of this is written, this is just, so just listen to me and believe me. So like, the population, the sample that you take, you want to make sure it's like a random sample. You want to make sure it is of decent size, so that your sample is actually representative of the population. Otherwise, it's not really representative. If you take like if actually the blood pressure of the whole population is actually normal, but your sample, you just chose to pick like 2-3 people of extremely high blood pressure, and you're saying, hey, these people represent the whole population, therefore the whole population's blood pressure is 2,500. Yeah. No. Okay, so that blood pressure doesn't reach that, but I'm just joking. But you get what I mean. That you gotta have your sample be representative. How do we know if our sample is representative? There's something called a normality test. A normality test. This normality test, we will cover it. It's basically a short test that, like, you'll just do it on Excel. You'll always start your tests with it, just to see whether your sample is more likely to be representative of the population or not. Like, you know, you just do some bit of a Excel hocus pocus, and it will find for you whether it is representative or not. Okay, that was just some probably not very organized, I apologize, not very organized information for you, just theoretical information about biostatistics and about this whole hypothesis testing situation as a whole. But let's go stepwise once again from now on. So basically, we have defined null hypothesis. What is a null hypothesis? It is the default idea. Null hypothesis, default idea, is the default idea that you want to test, that you want to see whether it is true or not. Okay, that is a null hypothesis. That's the default. That is the definition of the null hypothesis. Basically, default idea. And this default idea is gonna be most likely in the form of some sort of default assumption, like, you know, some default assumption about the population, and you want to, like, this sort of like status quo that you want to test, and you want to see, is it actually true or not. So the status quo and the default assumption you have of the males of Czech Republic is that it is 110. Okay, so that's the H0, your null hypothesis, is that they are indeed 110, and then you are going to test, okay, is it indeed 100? Is it likely? Is it more likely that it is indeed correct that their average is indeed 110, or is it more likely that it is not that way? Okay, so that's the gist of like what we're doing here. So the forms of null hypothesis, the form can be like in different forms. In different various forms. One form is, like we said, like one example is that what we just said is that a sample has the same mean as a population, so that the sample that you took is of males of whatever, or 110, and your assumption is that this sample belongs to a population who has indeed a mean of 110. This is one. Another example of null hypothesis is that if you get two variables, like two random variables, I don't know, like length, like how many hours a person sleeps a day, and their blood pressure, okay? And you want to see whether there's a relationship between these two things. And always your default assumption is actually going to be that there's no relationship between these two variables, and you are going to try to test to see, is there a relationship or not? And we'll get to each of these tests. Like, you have different so according to the type of null hypothesis and according to the type of context, you will use a different test to see to test this hypothesis. We will go through each of these one by one, all these tests, and you'll see what I mean. But so far we are going smoothly. We have defined what is null hypothesis. We have defined a bit more what is null hypothesis and give examples of what it is. And like we said, that in hypothesis testing, you're mainly going to be testing how likely it is the default idea, the null hypothesis, is true, as we've already said. If the p in this test, and you'll see what I mean in a bit. When we get to Excel, you'll understand this more. Is that when you do a test, when you run a test in Excel, it'll end up giving you a p-value. Okay, this p-value, just in summary, what is the p-value? Just to simplify it, it is like a value that tells you the likelihood of the null hypothesis. Okay, if the p-value is more than 5%, so if it's more than 0.05, you accept the null hypothesis. If the p-value is less than 0.05, you reject the null hypothesis and you take some alternative hypothesis in its place. Okay, so that's just p-value. And basically, so yeah, that's what we were saying, that in hypothesis testing, you're mainly going to be testing how likely it is the default idea, the null hypothesis, is true. If the p-value is less than 0.05, then you reject the default idea. If it's less than 0.05, you reject the default idea, you reject the null hypothesis, and you go for the alternative idea, the alternative hypothesis. So yeah, that is basically the gist of just this. This is the theory part of hypothesis testing. The next part that we want to cover is the types of tests that you will be running. But before that, just to finish off and clarify, whenever you whenever you're doing hypothesis testing, you always write down your null hypothesis and your alternative hypothesis. Okay, so that for example, in the example that we gave before about let's just keep it here, I'll remove it afterwards. So in the example we gave before, the null hypothesis was that the mean of the population's blood pressure is 110. The alternative hypothesis would be that the mean of the population is not equal to 110. All right, so that's always what you start with whenever you want to test anything. All right, so that's the null hypothesis and the alternative hypothesis. That is step one every time you want to do something. Okay, maybe I should put this somewhere, but let's just remove it for now. You'll remember it. And one more point to highlight is this point right here, that it's better to say that you reject the null hypothesis and take the alternative, or that you don't reject the null hypothesis. So basically, you say that basically to reject or not reject. That is the question. You don't say that you accept the null hypothesis or reject. No, you say you either don't reject, so I accept, but the way of saying it, it's better to say when you speak to the examiner, your answer should be that you don't reject the null hypothesis or that you reject the null hypothesis. Okay, that's just a side point. Yeah, so with that, we can just get right into it and see the types of tests. So first off, and this is your task in the test, and the first thing that you do in the test is that basically you're going to be printed a piece of paper and with some examples, just a sheet of paper, okay? And you're gonna, this is gonna be homework later on, but I'm just showing you as an example. They're gonna give you a sheet of paper, like one of these, like the question, and then a table, that is gonna be what the final looks like. What the Excel part of the final, that's what it looks like. And you're given the computer and do it on Excel, okay? So the first task, the first task that you have to do is you gotta identify what kind of test is needed. This is really, really important. There are 5 types of tests, and we'll go through each of them and explain how to recognize which test is required. And we'll also afterwards cover we'll then give examples of each of them as a sort of exercise. Then afterwards we will cover the Excel file, the PDF file, to practice each of them. So right away, so what types of tests are there? So first off, there's the one sample t-test. Okay, the one sample t-test, it is where one sample's mean is being compared to the population's mean. Okay, an example of this is that is the blood pressure of 16-year-old males 110. Okay, so you're asking, is the blood pressure of 16-year-old males 110. So basically, that's a typo, sorry, I wrote that wrong. So that you take a sample of 16-year-old males, and you check and you measure their blood pressure, and you see, are their blood pressures 110 or not, okay? In the test, you'd basically be given a table with a bunch of 16-year-olds and their blood pressures, and you put it into Excel and you see, is their average blood pressure indeed 110 or not? So yeah, so a one sample t-test is the test in which you are given a sample, like a bunch of 16-year-old males, and you're gonna check if that sample, their mean is 110. So basically, what it looks like is this. You've got the population, and you've got the sample, okay? And the question you're trying to answer is that, are 16-year-old males within the population of people within of 110 blood pressure? This is a very a tricky thing to try and understand. So I'm gonna explain it once again. I'm gonna explain slowly. Try to understand. If I'm not slow enough, just slow down the video. You can replay it as many times as you like. Trust me, I won't get tired because it's recorded. So you've got something called a sample, like I said. You've got something called the population. I know we explained population to be like the sort of the population is the thing where which you choose the sample from. Okay, that is one way to understand what is population. The other way to understand population is sort of group. Okay, so you're basically like population or like group. Okay, so what does this mean? So like when you draw a sample, when you take 16-year-old males, are 16-year-old males within the group of folks with 110 blood pressure or not? That is what you are trying to find out. So you're comparing the sample of 16-year-old males to and you're checking their blood pressures. And you're comparing this blood pressure of your sample to the population blood pressure. Okay, and you're trying to find out whether 16-year-old males are within this population or like group, are within the group, the category I think is the best word. Are they within the category of people with 110 blood pressure or not? That is what you're trying to find out. Are they within the category of people within 110 blood pressure or not? This is, I think, the best word that I have found that explains the situation, okay? So, you're given, this is the question that you're given. You're given a sample, and you are asked, are they within the category of folks with 110 blood pressure or not? And you run Excel to find out. So this is comparing sample to population, or like sample to population, or you could say to group, or you could say to category. I like the word category best. It fits. Like comparing the sample with some sort of category. So this category is folks with 110 blood pressure. Are they within that category or not? And you would run Excel to find that out. So that is a one sample t-test. So is a one sample t-test is the mean blood pressure of 16-year-old males 110? So like, are they from the population of people with a BP of 110? It's like population, or like, are they from the population like category, or like category. This is a bit ad hoc, but allow it. So are they from the population or like category of people with a blood pressure of 110? The next question, the next type of test is a two sample t-test. And once again, we're trying our best to recognize each of these. Okay, we're gonna try to recognize. Just we know, like just from the question, we find out what kind of test is needed. So from this, you are comparing a sample. 16-year-old males, you're comparing the sample to a category or population, which is 110, all right? So when comparing one sample's mean to the population's mean, like one sample to the population, you call it a one sample t-test, okay? Two sample t-test means you're comparing two samples, not to the population, not to the no, you're comparing them to each other. Okay, you're comparing two samples with each other. So you'd have like 16-year-old males and 26-year-old males. Okay, year-old males, and you're not comparing them. You're not comparing 16-year-old males to the category of 110 and 110 and 26-year-old males to the category of 110. No, you're rather comparing like this. You're comparing two samples to each other. You're comparing is the mean of 16-year-old males the same as the mean of 26-year-old males? So you're comparing two samples to each other. You're not comparing them to some external category, which is like 110 or something like that. Excuse my art. Like if this is Microsoft Paint. Trustworthy, reliable, but it looks a bit crude, but allowed. Anyways, so you're comparing two samples to each other. That is a two-sample t-test. Is the mean of 16-year-old males the same as the mean of 26-year-old males? And your null hypothesis, your H0, would be that they are. So the first mean is equal to the second mean, and your alternative hypothesis would look something like this, so that your the first is not equal to the second. It is that simple, right? That is your null hypothesis and your alternative hypothesis. Once again, I repeat, once you start your exam for Biostats, instantly the first thing that you want to do for Biostats is identify what kind of test is required. Is it one sample? Is it two sample? Etc. And then the second thing you do is that write down your null hypothesis and your alternative hypothesis. And then the third thing is that after you've written it, write down what your null hypothesis even means. Okay, maybe you could write down on the side what the definition is, but you don't need to do that. You can just know that by understanding. And write down what this means, like U1 equals U2. It would mean that the null hypothesis is that the mean of the first sample is equal to the mean of the second sample, okay? Another thing that you should do is that we'll get to that other point later after we reach it. I don't want to confuse you with too many points. So write down your null hypothesis and your alternative and understand what each of them mean. Each of them means. Okay. Anyways, one side point I wanted to mention as well is that always I've been given the example so far that is the mean of mean blood pressure of is the mean of the blood pressure of 16-year-old males the same as 26-year-old males? It doesn't have to be the same as. It can be is the blood pressure of 16-year-old males greater than the mean of 26-year-old males, or less than that of 26-year-old males. So you're just comparing them. It doesn't have to be is it the same as or not the same as. Like so here we wrote down the null hypothesis. Is it the same as? And the alternative would be that it is not the same as. Okay. So the other option is that is the mean of 16-year-old males greater than that of 26-year-old males? So the null hypothesis would look like this. The alternative hypothesis would look like give me my rubber. Microsoft Paint, very ghetto, allowed. The alternative hypothesis would be that the U1 is greater than U2. Okay, that would be the alternative. Okay. Likewise, if it was is the blood pressure of 16-year-old males less than that of 26-year-old males, this is what it would look like instead. Yeah. So the null would be that they are equal, and the alternative would be that the mu1 is less than mu2. Okay. That is all good. That is hopefully all clear. If you have a question, don't hesitate at all. And well, I can't really answer your question because it's recorded once again. But once again, you can repeat it as many times as you like, and I certainly won't get tired of repeating it. Anyways, I'm gonna stop with these puns. Probably I won't. I'm just gonna keep rolling these puns because I like them. So that's a one sample t-test. That's a two sample t-test. And like we said, the example of it is that is the mean blood pressure of 16-year-olds and 26-year-olds the same? Okay, so that's a one sample t-test. That's a two sample t-test. Now the next kind of test that you run is a paired t-test. A paired t-test. Okay, so this is a single sample, and you're viewing it in two windows of time, i.e. the same sample before and after some event. Okay, so that, the example is that is the mean blood pressure in a given sample, is it the same before and administering and after administering some drug, or before and after like some exercise or something like that, or like does the mean blood pressure increase after 2 hours of studying histo, for example? These are all examples of paired t-test, because it's always before and after. Okay, so one thing to mention, by the way, is that each of these tests has a sort of like anchor word to it, like, you know, like one word or concept that as soon as you see it, you know instantly what kind of test it is. Okay, for one sample t-test, for two sample t-test, like it's just through understanding, because you're comparing one sample's mean to the population mean, or to some categories of mean. Two sample t-test, it is two samples being compared to each other, like a sample of 16-year-olds and a sample of 26-year-olds. The paired t-test, the key word in it is before and after, before and after. So once you see like a concept of before and after, that way you know like that it's very likely that it's going to be a paired t-test, because it's a single sample and you're viewing it through two windows in time, before some event and then after some event. So for example, once again, so we write down here that let's actually make it look fancy, like my sample. Oh, it looks English, and we'll write down population here. So it's like, I like that, write down category now. All right, anyways, so the sample we're given is, let's just say, a sample of students. Okay, so a sample of students, and yeah, okay, there. So students, and there's gonna be some sort of event, and it's gonna be like studying histo, all right? And there's gonna be two events: students before studying histo, and students 2 hours after studying histo. Okay, so this is a list of their blood pressure, and this is their list of blood pressure 2 hours after. So this is a one sample t-test, because it is the same sample of people within two different windows of time, like before histo and 2 hours after histo. Okay, so now you are comparing their blood pressures. It is a paired t-test, because they are paired together, because it is a single sample. It's not a two sample, it's a single sample of students before and after some event. Yeah, so that is a paired t-test. So that is a paired t-test. We give the examples of it right here. I hope that's all clear. The next point is correlation. The next type of test is correlation. Okay, correlation, you have two random variables. Okay, you've got no control over them. Ultra highlight this. You have no control over them, and you're checking whether there is a relationship between them or not. Okay, so two random variables, by random I mean that there are two variables that you have no control over either of them. Okay, and you're checking whether or not I'm gonna remove that under my two random variables, and you're checking whether or not there is a relationship between them or not. So for example, is there a relationship between age and mean blood pressure? So can you control a person's age? No, you can't turn a dial and make me like a 10-year-old instead, or a 50-year-old instead. You cannot control it. When you think of control in this context, think of like flipping a switch or turning a dial. Okay, if you can't control it by flipping a switch or turning a dial, you can't control it. Simple as that. Okay, so in correlation, the two variables, you have no control over them. Okay, like you cannot control them by flipping a switch or turning a dial. You can't control age. You can't turn a dial to change the person's age. You can't turn a dial to change the person's blood pressure. Okay, don't try to think of some convoluted way to, no, just take it at face value. You can't just turn a dial and make a person increase or decrease their blood pressure just like that. Okay, so there's no control over either of these, and you're running the Excel test to find out whether there is a relationship between them or not. So the anchor for this is that you've got two variables and you can't control either of them. Okay, that's how you know it's correlation. As for regression, you have two variables. One of them is controllable, and you want to see if the other one, which you can't control, if the other variable that you can't control, you want to see if it changes, if it depends according on the controllable one. So for example, the example would be like the dosage of a drug versus how long, or like how to say this, the dosage of a drug, and let's say how long a person sleeps after giving that drug, like sleeping pills, okay? Like you want to see, by increasing the dose of the drug given to the patient, is he going, of the sleeping pills given to the patient, are they going to sleep for longer or not? Okay, so you're trying to find out, is there this regression, is there a regression relationship between these two variables or not, in which one of them is controllable, so the dose of the drug, you can control that by sort of like turning a dial, or like, you know, popping the pills. You can control that, yes, you can. But you can't directly control how many hours the person sleeps. You can't just tell the person, hey, sleep for exactly 7 hours. Like you don't decide that. You can't control that. Like you can't control that by moving a dial. Once again, like, you know, I'll give more examples on this in just a second, but that is the basic example, that one variable is controllable, the other is not controllable. And you want to see if the non-controllable one changes according to the controllable one, okay? Repeat that. You want to see if the non-controllable one changes according to the changes of the controllable one, yes? So, once again, another point to mention here is that the controllable one is independent. This is another name for it. It is independent, i.e., it doesn't depend on anything. It's just under your control. It doesn't depend on any other variables. It just depends on your control over it. So it is independent. All that it relies on is you changing the dial. However, the non-controllable one, you're trying to find, it is known as the dependent one, okay? Dependent in the sense that when I increase the dose, so that's the independent one, we want to find out if the non-controllable one, we want to see its dependency. This is the dependent one, like it would depend on the independent one, okay? This is it's a bit of a play on words sort of thing, so like take your time with this, it can get a bit confusing. Oh, I wrote something, okay, so let's see this example, i.e. when we modify the controllable variable, does the other variable change accordingly? There we go, perfect. I think this is a very good way to describe it. Yes, when we modify the controllable variable, does the other variable change accordingly? So that is regression. That is the concept. So correlation, two variables, cannot control either of them. Regression, two variables, one is controllable, and you're trying to see whether the other one changes accordingly. Does the other variable change accordingly? Yes, right there. So one example of this is that, does mean blood pressure depend on the dose of drug we give to a patient? Does mean blood pressure depend on the dose of drug we give to the patient? We can control the dose of the drug, and we are observing the mean blood pressure, okay? So one we control the dose of the drug, and one we observe mean blood pressure and see if it changes. Yeah, one we control and one we observe. We control the controllable one, the independent one, and we observe the one we can't control, the one that is dependent, question mark. Yeah. So, like, if we increase the dose of the drug, will blood pressure also increase? It's sort of like is there a relationship, like an inverse relationship, or a is there like are they, for example, like directly proportional to each other or not? That's the sort of thing I meant. Yeah. So some examples, some test examples for you. To see if you properly understand the topic. So first off, systolic, let's try and find out what kind of a test each of these are. So is it a one sample t-test, so one sample compared to a population or some category, two samples in which two samples are compared to each other, a paired t-test in which there's one sample which is being checked before and after, is it a correlation in which two random variables, you don't have control over either of them, no dial to control them, or is it two variables, one you can control and the other you can't control? Yeah. So the extra examples. So a systolic blood pressure in a population of smokers versus a population of non-smokers, are their means the same? Okay, tick tock, tick tock, tick tock. It is a two sample t-test because you're comparing two samples to each other. Like, so a sample of smokers versus a sample of non-smokers, and you're checking, are their means the same? Like, you know, so it would look like this. Like, don't worry too much about like in a population. Like this doesn't matter. The whole fact is that you've got smokers versus non-smokers, and it'll end up looking like this. Like this, just to complete the understanding. No, line like that. Oh, how do you do this? Yeah, like that. Sure, whatever. So it'd be smokers here and non-smokers here, and you're comparing them to each other. That is a two-sample t-test. So, next is there a relation? Is there a relationship already? Is there a relationship? So it's gonna be either what or what. It's either gonna be regression or correlation. All right. I'm always gonna like give a pause when I give a bit of a pause, like pause the video a bit and think of the answer. So is there a relationship already? You know it's gonna be one of these two between average heart rate and number of cigarettes smoked daily. Okay, what would this be? Tick tock, tick tock. It is gonna be a correlation. All right, you're checking for a correlation because you don't have a dial to affect the heart rate, and you don't have a dial to alter the number of cigarettes smoked. You're not going to go to patients and tell them, hey, could you smoke double the amount of your usual cigarettes for me? And you smoke no, you don't do that. So number of cigarettes is just a thing a person does, and average heart rate is a thing a person has. Two random uncontrolled variables. I want to see, is there a relationship between them? Next up, blood pressure in mothers and non-mothers, is the mean the same? This is tick tock, tick tock. It's literally the same as this one. Therefore, it's going to be a two-sample t-test. So the next one is a sample of smokers and non-smokers. Is each sample from the population and with mean blood pressure of 130? This is a very tricky one. Okay. Usually I'd cover this up. Okay, just yeah, look at it like that. Okay. So sample of, I'm pretty late in doing that. So anyways, sample of smokers and non-smokers. Is each sample from the population with mean 130? This is tick tock, tick tock, tick tock. This is one sample t-tests. Like these are like two individual one sample t-tests. Because you've got a sample of smokers and a sample of non-smokers, and you're comparing them to the and seeing if they fall into the category of the population of people with a blood pressure of 130. So it would look like, you remember we already covered this example. So these are smokers, non-smokers, and this is the category of dudes with 130 blood pressure, and you're comparing both of them to the population. Like you're comparing the sample to the population and another sample to the population. One sample t-test, one sample t-test. This relationship, this would be a two sample t-test, but no, this is a one. This is a one. Both of them are one sample t-tests, so don't get confused with that. So that's an example of two one sample t-tests. And let's go to the next one. Is the blood pressure of gold medalists higher than 110? Tick tock, tick tock, tick tock. All right, so this is obvious. This is clear again. Is the blood pressure of gold medalists? Gold medalist is your sample, is the sample, and you're checking if it falls into the category, the population of people with 110 blood pressure. So once again, he's repeating that it is a one sample t-test. But one thing they just said, is it higher than 110? So just the thing that would be different here is that your null hypothesis would be that their mean is equal to 110, and your alternative hypothesis would be that your mean is higher than 110. Okay, so that's the one difference here, that you're not seeing are their means the same between brackets or not. Is the mean the same between brackets or not? Here it's is the blood pressure of medalists, is it higher? So it's like, is it the same, or is it higher? Like, you know, between brackets, is it higher? Okay, so that is just the difference between the other examples. Yeah. So far so good. Sure hope I haven't lost you. Sure hope everything is clear so far. Take your time to understand. Really, it is simple. That like, if you don't understand the deepest details of it, just understand it. Like, you gotta understand this. You gotta understand types of tests and recognizing types of tests. Each one of them has a keyword. So even if you don't or a key word or a key concept and just practice, you'll find that it's actually very, very doable. It's very easy. You just got to get used to it, you know. Each one has its own anchor of a word, like, you know, and or a concept, and you just click, it clicks like that. Once you know your what type of test you need to do, everything else is smooth sailing. You just write down your null hypothesis, your alternative, and we'll look into that more in a bit. And you just go into this some like robotic Excel steps. Like, you just get used to the steps on Excel, and you are done. You are set. All right. So before and after seeing a horror movie, is the blood pressure the same? Tick tock, tick tock. Yeah, this is obvious. Before and after is a given already. So it is it is a paired t-test. So like before and after seeing a horror movie. Does sleep time depend on dose of drug we give? Tick tock, tick tock. This one's very clear as well. Does it depend on the? This is the key word right here. Depend. So that's just, what did I even do? Oh, okay, sorry. Yeah, I wanted to write something. Where is it? Yeah, just add this right here, there. Dependent. So does y depend on x? So I just highlight that just to make it extra clear. Okay. So oh no, now this is just jump. Okay, that's not. Anyways, does sleep time depend on dose of drug we give? Because we can control the dose of the drug, and it's just a matter of seeing how does this sleep time change accordingly. Yeah. So that is all good. That is all dandy, and onwards we go. Yeah, I'm insisting on making it all fit in one page. But anyways, so some practice notes, some practical notes that you should take with you. All right. So we'll go right through these. Some of these will make more sense after we actually do the practice on Excel, but let's see what we can understand from now. First step, always identify first what you'll need, what test you'll need for the question. So first step, always identify what test you need. Second step is write down your null hypothesis and write down the meaning of your null hypothesis, okay? And the meaning of your result. We'll actually get to that point in a bit. So write down your null hypothesis and the meaning of the null hypothesis when you get the question, all right? So these are the first two steps. Third step, always start with the normality test. Do not forget this. They always want you to start with normality. And we spoke just a bit about normality in the beginning. It is checking if your sample is a good representative, okay? Like I said, we don't take extreme like samples, like fringe samples, like samples on the far edge, and we're thinking that this will represent the population. This will be a good ambassador of the population. No, this is nonsense. This doesn't make any sense at all. No, rather you take a well-rounded, like middle sample, something that would represent the population. So always, and how do you check if your sample is more likely to be actually nicely representative of the population? You run the normality test. So next point, you already know this. If the p-value is greater than 0.05, so like if the p-value is greater than 5%, so 0.05, you don't reject the H0. Like you accept the H0, but yeah, it's better to call it that you don't reject the H0. And if the p-value is less than 0.05, reject the H0, okay? So it's really straightforward, and this is all you're doing. And then always remember, okay, you've gotten your p-value, you've decided on whether to reject your H0 or not, okay? Let's say you rejected your H0. All right, you rejected your H0. What does that mean? What does it mean when you reject your H0? This is very important. Understand what your result means, okay? And we'll get to examples of this when we get into practice very soon. Understand what it means to reject or not reject the null hypothesis, especially in correlation and regression, in which the null hypothesis is that the coefficient is 0. So in correlation and regression, we'll get to this, but the null hypothesis actually looks like this. It looks like null H0 is that beta equals 0, and the alternative hypothesis is that beta does not equal 0. Okay, so what does this mean? I'll give you a quick gist of this whole beta situation. I'll fetch the equation real fast actually. So we've got the equation right here, and time to get ghetto with Microsoft Paint. So the gist of the equation is that this right here, this beta, controls the relationship between y and x. And basically, if beta is, let's say that beta is 1, okay? If beta is 1, therefore, the more x increases, like if x was 10, y would be, let's just say for now that alpha is 0, okay? If x is 10, y will be 10. If x doubles and x becomes 20, y will also double and become 20. So this is a direct proportionality, okay? This is when beta is 1. When beta is -1, that will make, when x doubles, if x changes from 10 to 20, like x2, y would go into the negative, like, you know, so like an opposite relationship, okay? So what I wanted to highlight is that so long as beta is a number, so long as beta is like from -1 till 1 and anything in between, 0.5, -0, whatever it is, it's noting that x and y have a relationship between them, okay? X is the in this context, x is the thing we control, and y is the thing we're observing and seeing whether it's changing according to x or not. So x is the controllable variable and y is the non-controllable variable. Beta here, if beta is 0, therefore it won't matter. X can double, triple, quadruple, whatever it is, but y will not change, because whatever change happens in x, beta, it'll be multiplied by 0. Therefore, y will not change according to x. So, in terms of null hypothesis, the null hypothesis is always that there is no relation. What does it mean? There is no relation mean? There's no relationship mean. It's when h0, it's that h0 is that beta equals 0. So your null hypothesis is that beta equals 0, which means that the null hypothesis is that there is no relationship. The alternative hypothesis is that beta does not equal 0. Beta does not equal 0, and so there would be some sort of relationship. Is it 1? Is it -1? It doesn't matter so long as it's not 0. Okay. So when you reach the conclusion, when you check the p-value, and you find that the p-value tells you that when you find the p-value, look, you won't need this math, by the way. You won't need this math. This is just explanation for your overall understanding. By the way, important disclaimer. You just need to understand this part right here, okay, and the following that I'm about to say. This was just for some, like the mathematical explanation behind it. So, if beta equals 0, so like you got a p-value, okay, and your p-value ended up being, I don't know, 0.3, all right? 0.3. 0.3 is greater than 0.05. 0.05 is a point, okay? Since p is greater than 0.05, therefore, we accept the null hypothesis. We don't reject the null hypothesis. We don't reject the null hypothesis, therefore, we take this right here. We're not rejecting this, i.e. we're accepting this, and we're rejecting this instead. So when that happens, so a p-value greater than 0.05, this has told us to take this answer, okay? And this answer tells us that there is no relationship. Very, very, very important, okay? You could get the whole like answer and thing in practice correct, and then you don't know how to interpret your answer, and then it just flushes down the drain. So be careful and understand this point. When you accept the null, I mean like don't reject the null hypothesis according to the p-value in a regression question, and you accept, or like you don't reject, that beta equals 0, therefore you have decided that there is no relationship between them. Yeah? There is no relationship. So when you write down from the start, when you write down your null hypothesis, write down this null and the alternative, and just write down on the side, this means that no relationship, and this means that yes relationship. And just so that you don't get confused later. And then when you get your p-value, say that your p-value is 0.3, you'll take this, and you'll know that it means that there is no relationship. This is what you tell the professor at the end. I don't reject the null hypothesis. I don't reject the null hypothesis, and thus I have come to the conclusion that that beta equals 0, that is more likely that beta equals 0. Therefore, I've come to the conclusion that there is no relationship with a significance level of 5%, as mentioned in the questions typically. Yeah. So that is that. How about if the p-value was 0.045? All right. 46, sure, whatever, 0.046. This is still less than 0.05, all right? You don't round up, it's just 0. It's less than 0.05. Therefore, you come to the conclusion that you take this option. You reject the null hypothesis and you instead take the alternative, which says that beta does not equal 0, which means that there is a relationship, as we have written here. Yeah, so that is a better understanding of this whole situation of regression. Yeah, so that is that, and that's all good. I hope you understood that. If not, take your time. But the important part to understand is this part down here. Yeah, the part up here, you're not going to be asked about it at all. It's just for your understanding. If it helped you understand, yay, I'm glad that was helpful. If it didn't, then just don't let it confuse you. Ignore it. Yeah, just take this lower part and apply this lower part to your practice. So that's all good. Next up, so we continue onwards. So this was further elaboration on this point, that understand what your results mean and just like write your null hypothesis meaning on the side, like I said, so that you don't end up doing everything correct and then you end up interpreting your results wrong. This is a shameful, an unfortunate mistake is what it is, and it is very avoidable if you just know what you're doing. Yeah. So, like I mentioned here, i.e. understand what it means to reject or not reject the null hypothesis, especially in correlation and regression. So both correlation and regression have pretty much the same idea behind them, like I'd mentioned, like I'd drawn over there, in which the null hypothesis is that the coefficient equals 0. When the coefficient equals 0, which means that there is no relationship, okay? There's no relationship. So, H0 is that beta equals 0, and the alternative hypothesis is that beta does not equal 0, which would mean that there is an alternative, there is a relationship. Yeah, I hope that is clear, and that is all well and good. I'll keep this here. I'll just increase this size like that. Okay, so that's good enough. Anyways, onwards. These are more practical points. We'll get to these when we reach them. That be careful when highlighting, and be sure to highlight the title of the column. Otherwise, you might it might mix you up and might confuse you. So like when you're highlighting, be sure to, like, this is the title of the column, highlight this as well, and then select. You know, don't just highlight the numbers, but highlight from the top of the column onwards, from including the title. Yeah. Next point is that in the paired t-test, when you run the normality test, this one is more detailed, we'll get to this. When you run the normality test, you run them on the difference, okay? We'll get to this. 2-sample t-test, normality is on each sample. Then you run the f-test. We'll get to all of these. Then, according to the f-test, you select the appropriate paragraph. We'll get to each of these when we actually get to the examples. And regression, know which value is independent. This is from theory. From the start, you are trying to find out which is dependent, which is independent. From the start, when you see the question, decide which one can I turn a dial and control, and which one can I not control. We'll go back and revise these points once again after we have finished practice, because right now they might seem a bit not understandable, a bit abstract for you right now. So we'll get to practice. And right away, without further ado, we're going to go to practice. We're going to go step by step in how to do the whole Excel thing, like on Excel. So that was all some very important theory. Once again, you can find this Word file with its various modifications that have just happened right now in the video description below. And I'll also put there the 2 files that you'll need here, the Excel3 file and the instructions.pdf file. Okay. Oh, one more important point. It is unfortunate, but I think if I'm not mistaken, it's quite likely that if you are using a Mac computer, if you're using a Mac computer, you won't be able to work with this, because you have to enable macros on Excel, and this would only work on Microsoft Excel, and I think that requires a Windows PC. So if you're unable to do this, go to the Biophysics lab, and they have all of their computers. They won't mind that you use their computers, and practice Excel over there. Watch this video over there and just get your work done over there. Yeah. So we'll go to each of these. So fetch these files right away. Okay, I'll give you a second. You can have all the time you want. Okay, you can just pause the video and no, you don't have all the time you want. Don't waste time. Utilize your time in studies properly. Don't waste your time. Don't go taking a break now. You hear? Anyways, so get the files, and we'll start right away. In the PDF file, go right to example 1b part 3. All right. So example 1b part 3. We'll jump right to that. This is the file, and go to example 1b part 3 right here. All right, and this is what we are going to start with. So with this example, they have told us that the effect of stress on diastolic blood pressure was studied on monkeys. The stress was caused by electric impulse, the voltage of which in microvolts corresponds to value blah 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 blah. Okay, so basically they've given us voltage, okay, and the voltage is corresponding values of blood pressure are given in the table. Yeah, so basically this is the voltage, and they're telling us that this voltage, we are controlling it, and we're basically seeing if these electric shocks they are doing on monkeys. I don't know why they're doing that, and they were wanting to see if these electric shocks affect the monkeys. That's pretty evil science, I would say. But anyways, so what they're trying to see, what they're asking is that find out if diastolic blood pressure depends on the voltage. All right, I'm gonna give you like 2 seconds. Tell me what kind of test is needed here. 1, 2. It is clear. It is obvious. Find out if diastolic blood pressure depends on the voltage. Depends is the anchor word. Instantly, it is regression. And you've got voltage. We can control it with a dial. And blood pressure, which is just the following thing, the sheep. There's a sheeping behind, and we want to see if the diastolic blood pressure changes when we change the voltage. And so right away, I want you to think in your mind, what would be our null hypothesis and what would be our alternative? All right, so the null hypothesis is gonna be as follows. The null hypothesis for regression. For all the types of tests, is always going to be the null is always going to be H0 is that mu equals whatever number, and the alternative is that mu either doesn't equal or it's greater than or lesser than, according to how it's mentioned in the question. Is greater than, less than, or not equal to the number, whatever. Okay. In regression and correlation, you've got that H0 is that beta, and I think there's another symbol when it's correlation, but for regression is that beta equals 0 is the null hypothesis, and as for the alternative, it's that beta does not equal 0. And then, so we did the first step is that we chose what kind of test it is. All right. The second step is that we wrote down our null hypothesis. The third step when we want to answer these questions is that we must write down what the null hypothesis means, like what each of them means. So from now, we write down on the side that this means, like H0 means here that there is no relationship. Okay, and this over here, the alternative hypothesis is that beta does not equal 0, which means that, as we explained previously, beta does not equal 0 means that there is a relationship. Yes, relationship. Okay, allow my handwriting. So, anyways, so now we understand. So now we have the null hypothesis. We have what it means. We know what test we're gonna do, and therefore we've set up all the bases. Okay, we are ready to start. Okay. So to answer this question, first off, fire up Excel. For this, I'm just going to show you what it looks like. We go right to Excel. You go to your, where is it? There we go. You go to your clean copy of Excel 3. It's going to give you a few prompts. Okay. First off, it's going to ask you whether you want to enable editing. Of course, enable editing. The next point is that it's going to ask you macros about the macros. You do enable macros. Okay. So now your file is ready. All right. So let's just fix that up right there. Just adjust its size. Alrighty. And now we just go to the example that which one is it? Example 1. All right. Example 1b is the one that we're going to be working on. In the test, you're not going to be given like the tables already written. You're going to have to write down the tables yourself. You just write them, you jot them onto the table. Okay. We've enabled macros, and so now it's simply going to be a step-by-step process in which we are finding out in which we are applying the things that we need. Okay, first things first, before we do anything else. So this is a regression test, and we've written all our theory before already, right? So the first thing we're going to do, you can literally go right for the PDF file, and it tells you literally step by step what you have to do. I'm just going to be showing you it on Excel so that you're able to follow. But if you get lost at any point, or like later on if you want to revise or something, you can rewatch the video if you like. You can also just go right for the PDF file, and it'll go with you step by step about how to apply this. So first off, they didn't really mention it here, but first off we should check normality. Every time, it's always safest to check normality, okay? Check the normality of the values, all right? Check the normality of the sample, of the blood pressure, okay? The thing that we can't control, check its blood pressure, check its normality, sorry. The thing that we can't control, check its normality. So you just go for, you highlight it, you include the header, okay? You include the header right here, of the name over here, and all the values, you've highlighted them, okay? And then you press, follow with me, Control-Shift-S, and it gives you here, okay, number of the row containing the header. Okay, so this is the number of the row containing the header. This is it, right? Okay, so it's 2. Okay, that's good. Allow it. So then we select, use the mouse to mark one cell as the beginning of the output. This is basically where we want the output to be. Okay, that's a good place to put it. Sure, put the output. And we want, well, I want a normality test. Okay, 0 right there. Okay, 0 equals descriptive blah 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 normality. Okay, so just press 0 and it tells you right there. You scroll down and you have over here, this area is telling you about where is it, and we have it actually right there. Yeah, normality, I'm just gonna color it there, and you've got the p-value for the normality, and it's right there. Normality, it is 0.317. so since this is greater than 0.05, therefore it passed the normality test. Like these values, like this sample, it passed the normality test. Therefore, this is good. You should always start. I know in the PDF for regression, for this column, they didn't actually test normality, but I guess it's always safer. Always test normality from the start. They're always gonna check for it, So this is the first point. We checked for normality. Second point. Now we want regression. All right. So we want to check if there is the regression relationship between these two values. So we highlight both of them like this. All right. We highlighted both of them. Once again, Control-Shift-S. The row number 2 contains the headers. Okay. Where do we want the output? Let's just space it out a bit. Put it over here. All right. Now, what kind of test we want? Number 3. All right. You have the number. It's all very nicely programmed, the macro. So just follow its instructions. We want a regression. So 3, and now we want to tell it which is dependent and which is independent. So we have decided already that let's just put this away for a second, okay? Think with your mind. Which one can we control? We control the voltage. Since it is controllable, then it is the independent one. It's the one that we're not looking if it depends or not. We're not looking if it's following or not. We are the ones in control of it. So controllable equals independent. Uncontrollable is the dependent, okay? You get me? I'm not talking about dependent, independent in the sense of is there a relationship between them? No, I'm not talking about that at all. I'm just talking about, is it the independent variable in the sense that we are able to control it, or is it the dependent variable in the sense that we can't control it, okay? So we know that voltage is the controllable one. We just turn a dial and the voltage turns. So the voltage is the controllable one, and it is independent. So let's come back here. So let's say independent is blood pressure. No, independent is voltage. This one right here. We select 2 because 2 is that is telling us is the option which includes that the dependent is the blood pressure and the independent is the voltage. So like the controllable is the voltage and the not controllable is the blood pressure. So it's 2. Yes. Continue. And it's already given us our answer. Okay. Blah 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 blah. We can just jump straight to the p-value. All right. So we have right here where is blah 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 yeah, right here. So p-value, you can jump just straight to the p-value and highlight it. So the p-value is 4.20 times 10 to the minus 6. So let's just widen this. No, it doesn't change. Okay. Anyways, times 10 to the minus 6. So this is like 0.000000420. Okay. So it's really, yeah, you'll actually find it right there. Really, really small. So let me ask you, is this like, is the p-value greater than or less than 0.05? It is obvious. Okay. It is way less than 0.05. Now, what does that mean? Okay. What does that mean? What does it mean when the p-value is less than 0.05? That's a question for you. Tick tock, tick tock. It means that we reject the null hypothesis. Less than 0.05, reject the null hypothesis. Okay, so the null hypothesis, they've written it for us over here, all right? Right there. The null hypothesis is that beta equals 0, and the alternative is that beta does not equal 0, all right? So we have rejected the null hypothesis because p-value is less than 0.05, and we have accepted the alternative hypothesis. All right, we've accepted the alternative. And what does the alternative say? Like I said in the beginning, we did it right here. We checked what we already wrote down what it means when we accept the null hypothesis. So we accepted this instead of the null hypothesis. We accepted the alternative. We rejected the null. Okay, so we rejected the null. We accepted the alternative instead. So what does it mean when we accept the alternative? It is this meaning that we wrote right here. It means yes, there is a relationship. So that is our conclusion. So based on the Excel test we have done, we have come to the conclusion that there is a relationship between the voltage that we can control and the blood pressure of the monkeys. Yeah? So that is how you do it. Easy, right? So just to summarize what we've done, quickly, we just highlighted this. We ran Control-Shift-S and we did the normality test. We just did the normality test. Normality test gave us that the p-value for the normality test is 0.3. That's greater than 0.05. So yes, it is normal. It is correct. For the majority of the cases, like almost 100%. I don't recall a case in which normality has ever been like less than 0.05 in the exam. So if you got it lower, double check your answer, like double check your steps. You might have done something wrong. So p-value, okay, it is normal. Then we highlighted both of them. We did Control-Shift-S and we ran the regression test. It gave us this and we checked its p-value and it is less than 0.05. Directly we rejected the null and we accepted the alternative, and the alternative is that there is a relationship. Beta does not equal 0, therefore there is a relationship. That is done. We are done with example number 1. Okay, so example number 1 part B is okay. We're finished with this. So next part we're going to work on is example 2 part 5. So that is example 2 part 5. All right, so in example 2, the table below shows us the heart rate in a sample of 10 people. Okay, there is 10 people and their heart rates. All right. And part 5 is what we want to cover. Are the persons from the population in which heart rate is 72, all right, with 5% significance value? That just means that the threshold for the p-value is 0.05. That's all it means, okay? So, are the persons from the population in which heart rate is 72? This is a straightforward example of which kind of test? Tick tock, tick tock. Clearly, it is a one sample t-test, because you've got one sample, each person and their heart rate. Like this is a sample of people, comparing the sample of people to the population or the category of dudes with 72 beats per minute. So it looks like this. It looks like right there is sample, right there is population. So I like to say category from now on because I like that word. So and the sample is the people and their blood pressure and their heart rate. And the population is dudes of 72 heart rate, all right, of average 72 heart rate. And we're checking the relationship between sample and population, like this sample and population relationship. Instantly, this is a one sample t-test. It is simple. The H0, the null hypothesis, is that mu is equal to 72, and the alternative is that mu does not equal. Let's see the question. Are the persons from the population between brackets or not? Like, you know, are they or not, or are they not? So it's this is the null hypothesis, and the alternative would be that they are not. So they are not from 72. Okay, and we can write down what each of them means. So this the null hypothesis means they are from the population of 72, and the alternative is that they are not from the population with 72. Okay, and so we can jump right to Excel. It is example 2. You have them over here, all the tests. Very nice table they've prepared for us. So these are the persons. You don't have to run the normality test on the number of people, because this is just an index. This isn't actual values. This is just for identification sort of thing, you know. So we run normality on the heart rate. Okay. So once again, we highlighted, we included the header, and we highlighted. Control Shift S. Headers at number 2. Okay, at row number 2. Run the normality right over here. Sure. 0 is for normality test. Bam. Okay. And p-value is 0.3. So instantly it is set that it is normal. Yes. Okay. So once again, we want to run a one sample t-test. So we highlight again, we include the heart rate. We include the header. Control Shift S, and 2 for the number of the row which is contained in the header. All of this, I'm not making this up. This is all written in English, so you can read it each time you press a button. Okay, you can and then choose where the output is. And now we want to choose what we want. We choose we press 1 because it says 1. Press 1 for one sample t-test. Okay, one sample t-test, and now it's assume sample from normal distribution. This is basically enter the hypothesized mu. Enter the hypothesized mu. So they want. They're asking us what is what's the number we have in the null hypothesis, and as we got from the question, it's 72. They're basically asking for the category the category mu, or like the population's mu, the population's heart rate, like, you know, that we are trying to see, are these people from this population or not, in the population of people of 72 heart rate average or not. And so it is 72 is what it is. Be sure to enter that number right, because all of your answer afterwards depends on correctly entering that. Okay, and so we've finished that, and so we have here our null hypothesis is that well, very nice of them to prepare it for us. Our null hypothesis is that mu equals 72, i.e. the average of the heart rate is 72 indeed. And the alternatives is as follows. Now the alternatives. So they've given us all the options depending on the question. Depending on the question, we select a different frame to look at. So there's three options over here. Okay, 3 possible areas we can look at. This area, or this area over here. All right. So there's 3 places we can look at according to what the question is. They asked us, is it from the population 72? So it's like asking, is it or is it not? All right, so is it or is it not? This is what it is. This is what our alternative is, as we have already written. We've already prepared this over here. Yeah, already prepared this. This is what our alternative looks like. So is it or is it not? So this is the alternative. If they asked, is the sample of people of a population whose heart rate is less than 72, we'd look at this zone instead, and we'd look at this zone's p-value, okay? If they're asking if it's greater than 72, we'd look at this zone's alternative and this zone's p-value. Do you get it? It's very significant. It's very important. It's very important to to know what is your alternative and what is what are they asking you in the question. Simply just look at the question. Like, seriously, just look at the question. You'll find out very easily what it is that has to be which zone has to be checked. Yeah. So it's this one right here, the one that is mentioning that mu is not 72. So that is the alternative that we seek. So yeah, technically it's being, this is just to make this fully accurate, fully correct. Yeah, this is that, like that. There we go. So we choose this option right here, this alternative over here, and the p-value for this option is 0.19. So 0.19, what does that mean? Tick Talk, tick, tock. Yes, it means that it is greater than 0.05. Therefore, it means that we accept the null hypothesis, i.e. we do not reject the null hypothesis. So we do not reject this conclusion. Therefore, we take this conclusion over here that the conclusion that mu is equal to 72. So the final answer is that we can say with a 95% confidence level that this sample of people are indeed from a population of dudes with an average heart rate of 72. Yeah, so that is our final answer, and we are finished with that example. Is that okay? If you have any confusions, feel free to slow down, take your time, and look at it again. But it is really, really simple. That you just highlight the part and you run the normality test. Then you highlight the part again and run the one sample t-test, and you check which alternative corresponds to your question. And this is the one right here that we took because it said, is it from 72? And so we extrapolate that they mean that is it from 72, like, or is it not? Yeah, so is it not, as between brackets in our head. And so we choose this one, and so we check this one's p-value, and it's more than 0.05. So we accept the null hypothesis, i.e., like we say, we don't reject the null hypothesis, i.e., we do not reject the fact that with a 95% confidence level that this sample of people are indeed of a population of dudes with 72 heart rate. Yeah, 72 beats per minute. That is that example, and that's all good. Let's jump right to the next example. Let's just close this one here. Yeah. So that is okay. We are finished with this one. Next example, example 3, is that let's actually check it. Where is example 3? Example 3, right here. Yeah. So right on with it. So the next example that we have, example 3, is that the diameters in micrometers of erythrocytes measured in 2 people are as mentioned below. So person 1, person 2. This is their erythrocytes, okay? Their diameters. So the question they're asking, first point, is that are both persons from the population with diameter of erythrocytes 7.2? Focus, look clearly, and consider. What's the first step that we do in your head now? What's the first step that we do? We check what kind of test it is, okay? So what kind of test is it? 3, 2, 1. It is a look at it closely. Are both persons from the population? So we're comparing person 1 to the population and person 2 to the population of 7.2 micrometers for the erythrocyte. So these are 2 one sample t-tests, okay? Be very careful. We are doing a one sample t-test twice, all right? So that is it for this first question, all right? So let's get right to it. Be careful. Do you see how tricky that was? Not really tricky if you know what you're doing. So go right for it. First off, we write down, because it's like I said, person 1 and person 2. Let's just clear this first. I'm sorry for the mess. So person 1 and person 2, we're comparing each of their erythrocytes to the population or the of the category of dudes with 7.2 micrometers erythrocytes. Okay, so we're comparing person 1's erythrocytes 7.2, comparing person 2's erythrocytes 7.2. Okay, so we're doing a one sample t-test twice. So these are 2 separate tests. All right. So so you divide them, and then you go like H0 is that mu equals, and then 7.2, and H alternative is that mu does not equal 7.2. all right, now the rest is going to be very straightforward. It's going to be almost identical to the previous question that we did. It's just a one sample t-test, you do it twice. All right, so it's literally exactly the same as example 2, but we're just doing it twice. So you do one sample, you check the normality for this guy. I'll do it for person 1, and then you'll do it for person 2 yourselves. Okay, so you do person 1, you highlight it, Control Shift S. That's the level of the heading. Yes, it's number 3. Check the normality. Okay, pop it right there. 0 for a normality, as is all written in English right there. Ew, that looks ugly. I'm just gonna. Oh man. Okay. Look, I'm just gonna. Sorry, I'm just gonna remove all this because it started to look ugly. I'm just gonna select a different place for its output. So I'm going to repeat the same thing. Control-Shift-S, select all the values. Yes, 3 for the heading. Yeah, I'm just going to put it over here, just like over here. Yeah, that's better. And 0 for normality. Yeah, that's better. Okay, so it doesn't mess up the numbers. So the normality for person 1, for person 1's values, p-value is 0.9, so it's well above 0.05. Therefore, it is normal. Then once again, we highlight Control-Shift-S. Yes, the header's at 3. We'll put the output over here, and we want a one sample t-test. Select one for one sample t-test. Press 1, and what's the value of the mean that we want to test for? It's 7.2, and then we just check what is the result of the test. The question was asking, are they or are they not? So this is the null hypothesis. It's right here. It's written for us, and the alternatives are these 3 right here, right here. You don't have to. I'm just highlighting for educational purposes. You don't have to do the whole borders thing. I'm just trying to make it neat and understandable for you. So there's 3 options for alternatives over here. This is the one that we choose because is or is not. So is or is not. So is not is the alternative that we're choosing. We're not looking for a greater than or less than. Okay. So p-value is 0.4. 0.4 is greater than 0.05. Therefore, we don't reject the null hypothesis. Therefore, we go for that. Therefore, we take the null hypothesis with a 95% confidence level that indeed person 1's erythrocytes are from population of 7.2. Yeah, so that is the answer. So person 2, you're going to be doing the exact same thing. That is all. Yeah, so we're done here. Next part, like, are population means of the diameters of erythrocytes the same in both persons? Now it's different. Okay, what kind of test is this? Tick tock, tick tock. It is a 2 sample t-test because you are now comparing person 1 to person 2. You're comparing them to each other, sample to sample. 2 sample t-test. You are comparing these 2 to each other. So for them, this is what it's going to look like instead. Let me just clear up this. Okay, there we go. So person 2. So your null hypothesis is that the mu for 1 is equal to mu for 2. The alternative is that they ask, is it the same or is it not the same? So alternative is that mu 1 does not equal mu 2. All right. So we can do. So we can go right on with that. We can write down what each of them means. So we wrote down what kind of test it is. We wrote down our null hypothesis and our alternative. We write down what each of them means. This one means haha pun. Anyways, so the first one means that their means are equal. The second one means that the second conclusion, the alternative hypothesis, if we select it, would mean that their means are not equal. Okay, so we thus test them. We go right for Excel. We've done our preliminaries, and now we are going to test them. We've got to take person 1 and person 2. We're going to test the normality for each of them. We already tested the normality for person 1. Now we go and test the normality for person 2. Just for some. Let's just keep it orderly. This is for person 1, and let's put person 2 down over here. All right, person 2 normality. Okay, and this is just for it to look fancy and understandable. So Control Shift, we highlighted person 2. We already did normality for person 1. We're gonna do it for person 2 now. Control Shift S. Yes, the header's at 3. We'll put the output over here. We want a normality test, and person 2 normality is 0.8. It's well above 0.05. Therefore, it is normal. Done. So now we want to do a 2 sample t-test, like we had concluded in our paint drawing. It's 2 sample t-test. All right. So we highlight both of. So we highlight both of them. All right. Control Shift S. All right. Headers at 3, at row 3, yes. Output, choose a place with a bit of space in it. Let's just pick it over here, it's nice. Okay, and what kind of test you want? Press 1 for paired, press 2 for 2 sample. Okay, so we want a 2 sample t-test, all right? And it's giving us the results down here. They're right over there. That's our results. So before continuing, there's something very important to consider in a two-sample t-test. Be very careful. We've already done the normality for both dudes, then for both people, and then we got to do something before continuing. You're already gonna feel something's weird because you have something over here unpaired. Okay, like f-test, t-test. What's this? Then what's equal variance, unequal variance? What's going on here? Well, after we've selected both columns and we've done we've initiated the two-sample t-test, there's something that we have to consider first. Something's called the f-test. Okay, the f-test basically, in gist, it tells us are these two samples in this two-sample t-test, are these two samples compatible and comparable with one another? Is it possible to compare these two? And so, it's got something to do with variance and are the variances equal or unequal? I'm not gonna bother with the theory behind it, just because the practice part of it is extremely simple, and you won't need more than this. Basically, after you've run the two-sample t-test, you're gonna have something called the f-test, and it's gonna be right here. All right. And according to the result of this f-test, basically this f-test comes with this situation: a null hypothesis and an alternative hypothesis of the f-test. Okay. The f-test, the null hypothesis of the f-test is that there's equal variance, and the alternative is that there's unequal variance. And based on the p-value, you make your decision on the f-test, just like how we did with the normality test. All right. So in this f-test, we have come to the conclusion that we've found that the p-value is less than 0.05. What does that mean? That means for this f-test, is less than 0.05. Therefore, what do we do? Tick tock, tick tock. Therefore, we reject the null hypothesis of the f-test. We reject the null hypothesis and accept the alternative instead. Okay, so we accept this alternative. We accept that there is unequal variances. Okay, so this now makes sense. There's unequal variances. Therefore, and you have now two boxes. Okay, two boxes to choose from. Right? There's this box, and there's this box over here. All right. So let me just border them for you so that it becomes clear. So according to whether or not the p-value tells us to take the null hypothesis or the alternative, whether we come out with equal variances or unequal variances, tells us whether to take our information afterwards for the two-sample t-test from this box over here, or from this box over here. All right. So because we came to the conclusion that it is less than 0.05, therefore we reject the null and we accept the alternative of the f-test that there's unequal variances. So we do not take this one. We do not take this one, big X on that. We take this one of unequal variances. All right, right here. Yeah, it's written right here, unequal variances. And so we take the p-value for this one. Okay, so the null hypothesis they've given to us here, and we already know our null as we've written here. Our null is that H0 is that mu1 is equal to mu2. The alternative is that mu1 is not equal to mu2. All right. So H0 mu1 mu2. Yeah. So this is our null hypothesis. It is written for us right here. The alternative hypothesis. Once again, we have three alternatives. So not equal, less than, or greater than. You won't be looking at these because that's not what the question asked. If the question asked for it, go for it. Okay, is person 1 less than person 2? So you'd go for this alternative. This will the null hypothesis won't change, but the alternative is what will change. And if they asked you, is person 1's mean less than person 2's mean, this is what you would go for, and this is the p-value that would check. But no, they asked, are they equal? So it is are they equal between brackets in your head, or are they not? So this is the alternative that you would choose, and so this is the p-value that you would look at. And the p-value tells you that it is the p-value is greater than 0.05. Therefore, the conclusion that we make is that tick tock, that p-value is greater than 0.05. Therefore, we don't reject the null. We don't reject the null hypothesis, and we roll with it that indeed, with a 95% confidence, that mu1 is indeed equal to mu2 in these two people. Yeah, so that is your final answer. As we have seen right here, we wrote down already what it means to accept the null and what it means to reject the null, and we accepted the null. We accepted the null, i.e. we didn't reject the null, so therefore we took this conclusion that H0 is indeed, we take it, and therefore there is the mean in them is equal with a 95% confidence level. Yeah, so that is example 3 done for. Okay, so that is example 3. That is okay, and we move right on to example 4. Alrighty, right on to the next example. We're going for example 4. So what we got? So table below shows levels of digoxin in plasma of 9 people. All right. So level of some drug in 9 people it was measured 4 hours and 8 hours after an IV application. Okay. So already you got 4 hours after and 8 hours after, and it's a single sample of people. All right. Massive hint. All right. And now what they're telling us to use 5% significance level to check if level of drug 8 hours after application is smaller than level 4 hours after application. Okay, so first question is that which kind of tests are we gonna need? Tick tock, tick tock. It is obvious, like I said, the big hints. It's a single group of people, and it's the quote unquote before, and then after. Okay, this is like after 4 hours, then after 8 hours. So we're seeing the same sample through two different windows of time. So this is a paired t-test. Okay, a paired t-test. Yeah. So where this is the first window, and this is the 8 hours is the second window. Okay. So already we know that it is a paired t-test. So that's step one. We find out what kind of t-test we need. Step two is that we have to write down our null hypothesis and our alternative. Okay, so our null is that our null is that now the question is that use to check if the drug after application is smaller than 4 hours. Okay, so they want is 8 hours smaller than 4 hours. So as always, our null hypothesis is going to be equals, okay? And our alternative is what changes, right? So our null hypothesis is that after 8 hours is equal to after 4 hours, okay? Our alternative hypothesis is that after 8 hours is, what did they say? Is, check if it is smaller than after 4. 8 hours is smaller than 4 hours, okay? Easy, all right? And so, and we will write down the meaning of each of them. What do we mean by when we accept each of these? When we accept them, that means it's equal. It's quite, this one's quite straightforward. And if we take the alternative, it means that 8 is indeed smaller than 4. So like the equals here means basically that no, 8 is not smaller than 4 hours. Okay, so it's just, I don't know, I'll make a new symbol, not smaller than, allowed. Okay, whatever. Not smaller than, sure, you'll understand. So now we have the type of test we want, so it's paired. Now we have and we also have the null hypothesis and the alternative, and all that remains is to jump right onto Excel. So we've got the numbers here. In the exam, you would type down like the first column, you type down person 1, 2, 3, 4, 5, 4 hours, 8 hours, like that. In our current example, they've already written it for us. So 4 hours, person number, 4 hours, 8 hours. Okay. So first off, we check normality. All right. This is after 4 hours, after 8 hours. What we can do, there's two things we can do. Okay. For checking normality, we can actually either check each of their normalities separately. So like check the normality of this, check the normality of that, and then see. Or we can actually do something quite different that we do like 4 minus 8, like here, 4 minus 8 hours, okay? And we'd do this minus this, this minus this, this minus this, okay? And by that, and then we would run the normality on that, okay? So there's two ways to do this. Let's actually see what, this is how you do it in a paired t-test, and both of them work. In the table, in the PDF, they've written it that, okay, just as a heads up, the PDF, they've written it in a certain way. They've written it that they've written the null hypothesis that the level of the drug in 8 hours minus 4 hours equals 0, or it is less than 0. Do you get what I mean? It is like it's the exact same as this one, but the only difference is that like instead of this equals that and this is smaller than that, they've moved it over here. You know, so they've moved it like that. So 8 hours minus 4 equals 0, or that 8 hours minus 4 is less than 0. Yeah, but it should all end up meaning the same meaning at the end of the day. Anyways, the way they've done it, let me just check real fast. Yeah, the way they've done it is right here. Yeah, so 8 hours sorry, the way they've done it right here is that they've tested the normality on the differences, but actually it doesn't matter. Whichever you want to do, you can do. You can test each of their normalities separately, like we've done so many times. But I'm just going to show you what it looks like because we haven't done this before. So their differences, you can either do the Excel thing, which was like equals this minus this, like this cell minus this cell, and put the result here. So like equals, like equals this cell minus this cell, and you press enter, and then it'll give you, or you can just calculate it with your own head. 0, 0, like this minus this equals this. 0, 0, 0 0.2. Just do it right, okay? Please don't just do it right. 0, 0 0.1, 0 0.1, 0 0.1, 0 0.1, 0. All right, and then you run the normality on this, okay? And I'm just gonna run the normality on this. Control Shift S, headers on 3. Normality, I'm going to push it a bit to the side over here. 0 for normality, and p-value is right there, 0.6. All right, so it's already much greater than 0.05. So yes, it is normal. Like I said, you can instead run the normality on each of these separately, but yeah, it all works. It's all okay. Okay. Next point is we're gonna run the paired t-test. All right. Control Shift S. We selected both of them. Control Shift S. Headers at 3. Output, let's put the output like a bit over here. All right, just don't matter, make it look neat, please. Paired t-test is the one, and yeah, there we go. And yeah, now we just want to the H0, have they written it for us? They haven't written it for us, but we already know what it is. It's right here. Our H0 is that 8 hours is equal to 4 hours, and the alternative we're looking for is 8 hours is less than 4 hours. So 8 hours less than 4 hours, this is the one that we want. All right, this is the one that we want. Look at, like, when you're like the way that you find out that, you know, greater than, less than, if you don't want to confuse yourself, the arrow is pointing to the smaller one. Okay, so like, do you get me? So the arrow is pointing to the smaller one, so that means that this means that 8 hours is less than 4 hours. Likewise, it means that 4 hours is greater than 8 hours. Again, it's the same meaning. So this one, the symbol is pointing to the smaller one. It's like 4 hours is less than 8. So this is the one that we want. 8 hours is less than 4 hours. So we're looking at this box over here to get our answer, and the p-value is 0.1. So 0.01. And tick tock, tick tock. What does that mean? Tick tock, tick tock. Yes, that means that the p-value is less than 0.05. That means we reject the null hypothesis and we take the alternative instead in its place. We take the alternative, and the alternative is that 8 hours is indeed less than 4 hours. So the level of the drug after 8 hours is indeed less than 4 hours, and this is the conclusion that you say with a 95% confidence level of 95% level of confidence. Yeah, so that is our answer, and we have answered the question. So that is example 4. We are finished with it. Yeah, so that is okay. Next up, we got example 5. Right to it. Example 5. So size of red blood, yeah, more red blood cells, let's go. So sizes of red blood cells in micrometers for 2 people are as shown below. Okay, so I'm not going to read those numbers. So person 1 and person 2 create a sheet. Are the population means of the sizes in the 2 persons the same? I'm going to leave this for homework, okay, because this is literally the exact same as the one that we had recently done. Are the population means of the sizes of the red blood in the 2 persons the same? Okay, what kind of t-test? I'm just going to ask, what kind of t-test are we going to need for this one? Tick tock, tick tock. Yes, it is a 2-person t-test, because are the means of the red blood cells in the 2 persons the same? Okay, we are comparing the 2 samples, these 2 people, to each other directly. As always, we mentioned it as basically like, you know, P1, P2, and we're comparing them directly to each other, whether they're the same. We've literally done this question already. Don't get confused by this word right here. Are the population means of the size? It doesn't really matter, because it ends up that are the population means of the size of red blood cells in the 2 persons the same? We're comparing the 2 persons. Are the 2 persons the same? We're not saying that are the 2 persons from the population of 7.2. In that case, it would be compare person 1 to 7.2, compare person 2 to 7.2. So that would be 2 different one sample t-test. This is a two sample t-test because we're comparing is person 1 the same as person 2 in terms of their means. So we're done with that. The null hypothesis would be that tick tock, okay, would be that person 1 equal the mu of 1 equal mu 1 equals mu 2, and the alternative would be that mu 1 does not equal mu 2. Okay, we're done here. So next example, right to it. 5, we're just gonna say that it was okay because we've done it already. Example 7, where is it? Yeah. Example 6, what was example 6? Yeah, okay, example 6, I'll just leave it for homework as well. You can do that. Example 7, all right? So in example 7, you got a table below shows values of hemoglobin and PCV, packed cell volume, okay? So the amount of hemoglobin and the volume of the cells, all right? Taken from 20 randomly chosen women. Find out whether there is a relationship between hemoglobin and PCV, okay? What kind of test is this? That's the first. So step 1 is always what kind of t-test. Step 2 is write down your null hypothesis and your alternative. Step 3 is write down what the null and the alternative mean. Step 4 is run normality. Step 5 is run your test. This is how it is, okay? So write with it. Step 1, what kind of t-test is this? Tick tock, tick tock, tick tock. It is clearly it is correlation, because we can't control either of these. Can we go to the woman and say, hey, can I press a button on your forehead which changes the level of hemoglobin on in your blood? No. Okay. Can I change the volume of your red cells, please? No, you can't do that. There's no dial that you just turn around to modify these. Okay. And the way that it's phrased as well, in regression, it would sound something like does the hemoglobin level depend on the volume, or something like that? That would be regression. No, this is two variables that we don't have control on either of them. Yes, so that is clearly correlation. All right. So already we have our we know what kind of t-test it is. It's going to be, once again, it's going to be correlation. What kind of so that's the one, what kind of test it is. Second step is that what is our null and what is our alternative. So our null is that whatever it is, like beta equals 0, but it's not going to be beta. I think it's a different letter that they use for correlation, but whatever, we'll just use beta for now. Beta equals 0, and the alternative is that beta does not equal 0. All right. So that's step 2. Step 2 we're finished with. Sorry, I'll not put a tick there. Step 3. What do these mean? What does each one mean? The null hypothesis, beta equals 0, means that there is no relation. The alternative, beta doesn't equal 0, means that there is a relation, okay, between them. So that is what the thingies mean. That is what the null and the alternative mean. So no relation, and yes relation right here. Yes relation. Allow the Microsoft Paint. Yeah, okay. So anyways, so we've got that on step 1, 2, 3. Step 4 is run normality. So we go right into our Excel file. We write down this table into Excel. It's already prepared for us right here in example 7. We run normality for each of these. All right. So you highlight it, including the header. Control Shift S. Headers at 2. Yep. Put the normality in somewhere decent because we want to look ordered. 0 for normality. Okay. Blah 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 blah. It's almost always going to be. In fact, I don't know an example of normality being incorrect. So yeah, done. So the hemoglobin is normal. Highlight this. All right. Control Shift S. Headers at 2. As you see, always remember to highlight the header because it's always going to ask where have you put the header. So it's better this way. Control Shift S. Blah blah blah. 0. Blah 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 blah. Normality 0.28. 0.218. It's greater than 0.05. Normality. It is normal. Done. Okay. So now we want to run correlation. We highlight both of them. Control Shift S. Headers at 2. Yes. Where do we want to put it? Let's put it down here. All right. Which test do we want? Press 4 for correlation. There we go. Press 4. Press OK. All right. And we put it down here. Correlate. Right there. Correlation. And so yeah, that's the number. That's row. Okay. The null hypothesis is that row equals 0. rho is exactly the same as beta, but it's a different equation. Rho equals 0 versus rho does not equal 0. That's our thing, that's our alternative, and the p-value is right over there. It's very easy. It's ultra small, 0.000, because e to the minus 6, like that means that 1.45 times 10 to the minus 6. So that's a very small number, 0.000000145, something like that, like, you know. And that number is far less than 0.05. What does that tell us? Tick tock, tick tock. That means we take the alternative hypothesis. We reject the null hypothesis, and we take instead the alternative hypothesis, which is that rho does not equal 0. If rho does not equal 0, therefore, what does it mean when rho does not equal 0? Rho looks like this, by the way, just a side point. What does it mean when rho does not equal 0? It means that yes, there is a relationship between hemoglobin and PCV with a level of confidence of 95%. Yeah, so that is that easy example, and we are done with that. And that leaves us with pretty much the end of the seminar. This is just homework for you. Get a good look at it. Screenshot it if you want, or whatever. And or you're gonna have this in your file. That it's gonna be in the description below. So just go for that. Practice these, and yeah, that is it. I'll go back to this part over here, the practical notes. Maybe they'll make more sense to you now. Identify what you'll need for the question, what test you'll need for the question. As we said, then you write down your null hypothesis, and then mark to the side what your null hypothesis means. Then run your normality test. Then run the test accordingly. Okay. If the p-value is you already know this point and understand what your results mean. Okay. Some side points as well. Be careful when highlighting. Make sure to highlight the title. Make sure to highlight the header. Okay. Paired t-test. The normality is done on the difference, but this one is like you can do it either way, actually. Two sample t-test. Remember to run normality on each sample. Then f-test. Remember the f-test. Okay, it's gonna be difficult to forget it, actually, because once you run the two sample t-test, you'll see f-test, then two boxes, equal variance versus unequal variance, and to find out which one you choose, you follow the f-test. Yeah, it's all gonna be right there in front of you. Regression, know which value is independent, like under your control, and which one is dependent. Okay, we are finished. That is all for the seminar. I hope that it is helpful for you, and I truly wish you all the best, and have a nice day then. All the best for your studies.